Welcome to our PCB layout tutorials. Now during these tutorials we'll be following 4 different steps to design our PCB layout. The first step will be designing a schematic and testing for functionality. The second step it will be designing our PCB layout, which is the mission for this tutorial, or you can call it the objective. The third step is to generate Gerber files. Lastly, we'll do panelization of our PCB. Now the software that we're going to use is called Proteus. The version that I use is Proteus 8.6. Now let's start from the beginning of how you create a new project. To create a new project, you go to File, New Project, then name your project accordingly. So I will name mine PCB1 layout. The destination folder where I'll save my project will be under Documents. I'll create a folder, then call it, here's a folder already, PCB Tat 1, then go to Next. The wizard now will ask you on the template for your schematic. Now normally I prefer to use Landscape 8-Ray. You can choose any other template that you think you need, but all of them, they depend on the size of your PCB that you're going to create. Because this is simply going to be a tutorial, any layout pretty much will work. So I'll go to Next. Then it will ask me if I need to create a PCB layout from the selected template. Yes. Now what kind of PCB do I want to design? So as a start, we all need to start with creating a generic single layer. So this is the layer that I'm going to select. Next, and lastly, if the project is going to be firmware based, no firmware required. Now this is the summary of everything that we need for our project. Finish. Now when it opens, it will start opening from the PCB layout side. We'll go back to the schematic capture. The schematic capture, this is where we're going to start creating our circuit and testing for functionality. The PCB layout, this is the side where we're going to design our PCB layout. So let's start with the schematic capture. Now the circuit that we're going to design, it will be PWM using a 555 timer. The first component that I'm going to look for is a 555 timer. So I'm simply going to type the keyword 555 timer. Then I will see all the components available. Then double click, it will be added on your devices. We need a potentiometer, we obviously need a resistor. I'm going to select a generic resistor, capacitor, electrolytic, general purpose. Okay. Now to drive our load, we'll be using a power transistor. Okay, in this section, already I've selected all the components that are required to create our PCB. I've also included the measuring instrument, which is the oscilloscope, power sources. So I'll be showing you where to find this for analysis. Now the power sources will be found in the terminal mode. If you're looking for positive power supply, you will select the power source. The ground, this ground can be found as a normal ground as well. Now I have a NPN transistor for driving my load, which is a 12-volt lamp. On the oscilloscope, I'm showing the output of the PWM. So I'm just going to check this for you so you can see how it is expected to work. Okay, on simulation, I'll be varying my duty cycle using the potentiometer. Okay. And I can see when I vary my duty cycle, the period does not change. The only thing that changes is the T on and the T off, which means the PCB is ready to be transferred to, the schematic is ready to be transferred to the PCB layout. Now on the PCB layout, the first thing that we're going to do is to draw our board edge. Now to draw the board edge, you first need to select the shape, then select board edge. Now you can be able to draw your board edge. It's not only limited to square shape, you can also do your circles, you can do all other shapes. Okay. Now you also need to know the dimension of your board. I'll be measuring the size of my board. Now according to this, my board is going to be 4.5 centimeters in length, and in breadth it's going to be 3 centimeters. Now all the components that can be able to fit, especially the 555 timer. Okay, I'm simply going to put in the 555 timer as my first component. Then I'll place all other components as well. Now there's one good trick that I normally use whenever I'm placing the components. The first trick is how I'm going to place my components going to be next to the components of the pin legs that are interconnected. This will limit the time that it takes to root. That is trick number one that I normally use. Now let's see, we'll be starting working from pin number 2 to pin number 8. I can see that pin number 2 is connected to pin number 6. I'm not going to root this now. You can see already there's a direct link. This blue line, it shows you the direction if you're going to root, from which point to what point is it going to be routed to. Now I'm going to remove this so that I can be able to start afresh. Now let's place all our components. The first component, it will be on pin number 3, which is an NPN transistor. So my NPN transistor is Q1. I'll place it first. Okay. I'll increase the board edge as it's a bit bigger. Okay. Now from this component, you can see there's a circle and also another circle with gray shaded area. Now this component tells you that this is a through-hole component. If it's not a through-hole, this is what you will see on the pick list. I'm simply going to use any component. Okay. Now this is a trimmer. You can see this shows you that this is a surface mount component because they will be mounted on top of the board directly. There's no soldering by hand that is necessary. This is normally done by pick and place and the reflow oven. But for the method that we're going to use at the end, we normally require only through-hole components. So all the components that I've selected, they're all through holes. Now you can see there's also components that does not have the PCB package. If it has a red cross like this, it simply means the component does not have a well-defined PCB package. You can either decide to create your own PCB package, or you can force another package, but I'll show you how I deal with this easily. Now let's continue. Pin number 4, I have R1, which is a 10K resistor. R1 connected to pin number 4. So this will be my pin number 1, then there's my pin number 4. There's my 10K resistor. Pin number 5, I have a capacitor going to ground as well. So there's C2 on pin number 5. C2 pin number 5. Likewise, we continue D1 and D2 next to R1. There's D1, and I'll also place D2 to increase the size a little bit so that I can place them directly where they're supposed to be connected. Okay. Now, following is our potentiometer. Now this potentiometer, we can see RV1 does not have PCB package. So this is how I'll be dealing with this. I'm going to select another PCB footprint. Now this will be, you can look for discrete components, but normally you look for quite some time before you can find the through hole. But if you decide to use connectors, it becomes way more easy. So I'm going to use a connector that has only 3 pins. Okay. There's my connector. I normally prefer this, since it's a potentiometer, to be at the far end. Then follows our C1 next to my RV1. C1 connected to my RV1, I'll rotate. Okay, and L1. Now you can see if I try to place L1 as well, it does not have the PCB package. So I'm gonna try using header connectors from this side. Now I cannot find the header connectors from this side. So I'll be going to my schematic to change my component. Since I've already confirmed that my circuit is working in place, I'll be placing my header connectors. Okay, I'm looking for a 2-pin header connector that is through hole. Now this header connector, it will be in a place of my lamp. Okay, there's my header connector in place of my lamp. Okay, let's rotate like this. Okay. Now, lastly, we also need to know how are we going to connect our VCC and our ground as well. Now, VCC and ground, I'm simply going to use another connectors in place. Okay. Now my jumpers have been connected, J1 and J2 connected respectively. There's J1 and here's J number 2. Now let's see what this PCB would look like. So to be able to visualize our PCB before it's being manufactured, we use the 3D visualizer. Now in the 3D visualizer, this is how our PCB will look like. Underneath the components, the holes, the pads, and all that is required. And then on top we have our components. Now, since we changed our size of the PCB, let's do other measurements and see what is the size of our PCB. So this looks to be 4.5 by 4.5. Let's see, there, 4.5 by 4.5 centimeters. Okay, now I'm going to remove this so that it won't be added to my PCB. Now, what happens if we don't have the board edge? If we don't have the board edge, currently you can see our board, it has the green layer. If I remove the board edge, this is what you'll see, just components floating on space. That's why we always start with the board edge, so that we can be able to determine the size of our PCB. Okay, now I want us to begin routing. So to route, we go to track mode. Remember, when you're placing the components, we are on the component mode. This is the package mode to be able to see the packages for all the components and the sizes. Normally, almost all softwares, they normally use inches instead of centimeters and millimeters, but mostly South African metrics, they use millimeters. Okay, now let's go back to the track mode and begin routing. Now, when I route, I also have to consider the size of my routes. For an instance, if it's T4, this is the size of T4 route. If it's going to be T10, you will see that the size, it changed 8-bit. Now, the more I increase the value of my route, you can see the size, they also increase respectively. Now, size of your route will also depend on the components that you're going to use. If it's a power circuit, obviously more current is going to be flowing through the circuit, you'll need bigger route. If it's frequency signals, you'll need smaller routes, but those we'll talk about them during our practicals. Now let's go to our routing part. Now when you talk of routing, we simply mean connecting the copper from one component to the next component. Currently under the board, you can see there's nothing. If I add one route, if I go into the track mode, selecting 25 as my personal preference, when I go to the 3D visualizer, you can see there it is. Okay. Now let's continue. So I'll be routing all of these tracks. Now I'll route the tracks which are direct first before going to routes which are 8-bit tracks. Okay. Direct number 2, pin number 6, connected. Already I know all of this. They're interconnected. Okay. That is a bit far. Let's see this one that goes around C2. see two connected, and let's look at these two. As well, try to align them so at least they make my board to be a bit neat. Root. This one as well. Now let's see how we get root. Okay, I'm only left with this root. Now in this root I'll be showing different kinds of errors, and this error is it will be able to cover most of the rules that have been violated. Okay, now first we can see that this root, it says connectivity status 1 missing. When I'll double click, it will take me to show me where this is being connected to. Now let's see when I root the very same track that is giving me error. And I can see it's not that simple to root that track. And then, okay, let me remove this one and root it directly so you can be able to see. Now, again, there pops up a lot of errors. When you double click from error to error, it will show you where's the error. Error number 3, error number 4 next to it, number 5 next to it, 6, 7, 8, 9, 10 as well. Now, how do I fix this root? I can opt to add a jumper. I can opt to use the auto router as another preferred method. By using auto route, I'll be going to auto router, then begin routing automatically. Now that route will be routed directly to that point, and besides, those are the only routes that are left. Okay, let's remove the size. Let's reduce the size. Take it there. Then introduce the routine. Then fix the error. The error has been cleared. Now, since we can see that the error has been cleared, then this is our PCB. If we're happy with it, we go to the next. Okay, now that we are happy with our design, we're going to add some features. Now, the first feature that we're going to add is the zone. Now we're going to use the default zone from top left corner to the bottom left corner of the board edge, then connect this zone to none. Where is the zone going to be? At the bottom copper. Now I'll show you what is the zone. The boundary, let's leave it default, relief, solid, the clearance as minimum, still fine as possible. Then okay, now you can see we added the blue layer on the board. Now if you go to the 3D visualizer, now our layer has changed. The space that was not previously occupied, it means that was the copper that we're going to remove. The space that is currently occupied, that is the copper that we need. Which simply means we only need to remove the small copper around this part, this tracks, and that's all. Again, the difference, if I remove the zone, this is the copper that we need, which means the last part of the board is going to be etched. The copper that we don't need is going to be removed. Rather, we keep the zone and just remove small amount of copper on the board. Now let's go to the next step. The next step is to create the Gabber files. The Gabber files are created by go to the output, generate Gabber acceleration file. Do you want to run the pre-production check now? Yes. That will check for all the errors on the PCB, if there's any design rules that have been violated or not. Now everything is well. I'm going to close this. What do we name this? PCB layout 2. Under the very same folder, what kind of files do we need? We don't have any top copper because we're creating a generic single layer. The bottom copper, the top silk we need. What is the top silk? As you can see, there's components drawn on the PCB. Now this will be drawn by the silk screen. The top resist, we don't need the top resist because we're only going to solder at the bottom copper. The top assembly, the board edge is needed as well. Make one, the board edge, and the drill files. Okay, then I'm going to produce this as a txt file. So if I'm going to produce them as a txt file, this is what you're going to expect. Okay, now I'm going to open with Notepad because this is a txt file. Now you can see this is all that can be found, just the coordinates. However, if I open this with another software called the Altium Designer, and also the Proteus, I'll open to the Proteus as well so that you can see. One thing that I like about the Altium Designer software is that all those files is going to separate them and show you individual files. Now this is the bottom copper, the solder resist, the drill files, the board edge, the components on top, and the silk screen. Now these are different files separated, but they're from the very same PCB. All these files are going to be needed by the person who's going to the PCB assembly. Okay, now you've seen that if you open the Java files as txt files, we only get the coordinates. If we open with Altium, we'll get different kind of files where the files will be separated individually. Now if you open the Gerber view, this is what you're going to see. Now you can see that the layout now is not the very same as the one that you've seen in the 3D and the PCB layout. Each and every file has now been considered and they've been embedded together to form one complete file. So let's look at these files from this side. This is the silk screen, light blue, I think it's aqua blue, the sky blue, this is the copper, the red, this is the silk screen as well. Okay, the board edge is also blue. Now this is the Gerber view. Now the last part will be us creating panelization of our PCB.